All right. So, hi everyone. Glad that you all joined today. My name is Chris, and today I'd like to talk a little bit about my a side project that I'm working on, and I'm working on building a boot menu in Linux Boot, right? So, how many of you are in host firmware development? Like a couple of people are working on that. I know these guys are working on that for sure. Yeah. All right, cool. Some of you heard of Linux Boot already? I know that you know, right? Okay. All right. So let's see how we can work through it, right? Yeah. So my name is Chris. I'm working at Nine Elements. I do a couple of things. I'm part of the foundation. I have another company that does firmware testing, and I'm part of OCP and so on and so forth. So my work days and my weekends kind of span around firmware. So on that. So to get everyone on the same page, right? So how do we boot, right? So it's a very simple question, and a couple of people probably saw that picture already. It's from the code documentation, right? But it doesn't really matter what firmware stack we're looking at. If you're looking at UEFI or if you're looking at coreboot, U-boot, whatever, right? You always have like a couple of stages that you're going through, and at some point in time you kind of land somewhere here, right? And somewhere here is a bootloader that loads your operating system in the end. So if we wanna simplify that, right? So, and that's like highly incorrect, but if we want to simplify that, we do that, right? We kind of bring up the hardware, and we do some stuff, right? It's platform dependent and SOC dependent and whatever, and then we have a bootloader that loads into our target operating system, right? So you load Linux or Windows or whatsoever afterwards. So, and the idea of Linux Boot essentially is that we still have all the hardware initialization part, but what we're doing is we're putting a Linux kernel and an init-rumfs into the firmware, right? So instead of booting, going to the BDS phase of UEFI or loading some other bootloader, we are directly loading Linux Boot. So directly loading a Linux kernel, right? That loads an init-rumfs. That's what's in the process. So if we are thinking about that simplified boot flow that I just showed, it's essentially that, right? So we still have the hardware in the part, obviously. And however, now we have a Linux kernel that we'll load directly after the hardware's up and ready. That Linux kernel kind of loads an init-rumfs. And that kind of spots an init process. And that whole thing here at the end, it's called Linux Boot, right? Because it kind of makes sense. We're booting in a Linux kernel in firmware, so that's Linux Boot. So what is actually an init-rumfs? I'm not sure how many people work around that normally and how much you care about init-rumfs and these kind of things. But if you look at the this one. Yep. Oh, yep. Right. Does it work? Yeah. Can you try again? Yeah. Okay. Yep. All right. Now do we need a mic? No. No, it does work. Yeah. I kind of have to eat it in order to. All right. Anyways, does that work for you in terms of sound? Yeah. Perfect. Okay. So, as I said, right, what is actually an init-rumfs? So now I'm, incapable of moving here, right? So you have to work with that. So what is actually an init-rumfs? And if we're looking at how a kernel boots, it kind of once the Linux kernel is ready, it hangs in this, in initramfs, which is like an initial RAM file system, as a temporary root file system. And that temporary file system kind of contains all the drivers and tools and initialization scripts that you essentially need in order to find your root file system and to change root into that root file system, right? So for Linux boot, it's kind of the same still, but a little bit different, because instead of finding only the root file system, we're actually trying to find the target operating system, right? So that makes sense, because when we are in Linux boot, we are still in firmware, right? So first of all, we have to find all the devices that are actually there, and have to mount those devices and see, do we have a Linux kernel there? Can we boot into something or not? And once we find something, we can actually boot into that, right? So initramfs is kind of so initramfs is kind of a important thing to have, and that's kind of a standard thing that you have on every Linux operating system. Something that I just talk without the microphone. So something that we worked on as a community is U-Boot. U-Boot is an initramfs builder. So there's a couple of issues, let's say, or it's a little bit hard to build an initramfs itself, right? The issue here is that for free, and that means footprint in terms of size, right? So in firmware we really care a lot about size, and if you don't have to put in the dependencies because they are already in you get that with a very small footprint, right? So if you want to build something like a boot menu which potentially has. Hello. Yeah. And that is potentially very helpful if you want to implement something like a boot menu. So how does that work, right? So what does uroot do in order to compile everything together into a single command, that kind of share all dependencies? So as I said before, uroot contains a lot of commands that we re-implemented that are standard Linux commands, right? So if we're looking at the, if you're downloading uroot, like the uroot repository, you will find a commands folder, and in that command folder you will find like boot commands and core commands and these kind of things. And in the core commands we can essentially find the core commands, right? So that means like we implemented cat, we implemented copy, change root, bind, and so on and so forth. Everything that you could potentially need. And now if you're building an init run with S, which essentially works like that, you call uroot, right? So you call uroot. You have to define like an output where that init run with S should be placed when it's built, right? You define a couple of commands that you want to have to build in, right? So in that case, I said, okay, I need block ID, cat, change root, copy, dd, and these kind of commands. I want them as binaries in my init run with S. And I add another command from the experimental folder, which is cbmem, because I'm working with coreboot, right? And I wanna access the coreboot memory, the coreboot tables. So I can build that all together, and what uroot does is it takes all the individual commands, right? That like copy and dd and so on, copies them into the temp folder, and rewrites these commands into Go packages. And then it creates a new main Go file, like a new main file, and compiles everything together. And now when you're calling that newly compiled single binary, we kind of distinguish what command should be executed based on the arguments that you're actually putting in. So how that looks like how that looks like in uroot is, so if you build an init run with S with uroot and boot into that, you essentially have all the different commands like IP and DD and so on. However, they are all linking to the same binary, right? So you got like you always execute the BB binary. However, we are distinguishing what gets executed by whatever you called here, right? So if you called IP, we are kind of looking up in the BB binary, okay, what is the IP command actually doing, and calling the IP command in that single binary, right? So that's pretty neat. So how does it help now? I was talking now 15 minutes about uroot and compiling it all together and so on and so forth. And the key point here is, right, so if you kind of fell asleep like the last 10 minutes, the key point is really we're compiling everything together into a single command. This leads to that individual commands are actually sharing dependencies, right? And that's like the key point. And uroot already has a lot of dependencies because we got a whole bunch of commands already in there. And that means maybe we can use some of these dependencies that are already there to build our own boot menu, right, or to build any other program that we want to build. So, and while I was thinking about how I should build my boot menu, I saw that we have the standard uroot shell, right, the POSIX style shell that we're using in uroot. So the one that you're dropping in if you're booting up the system is Gosh. And Gosh actually heavily relies on a library or a framework called BubbleT. And BubbleT is a library that allows you to build terminal user interfaces. And that BubbleT has an Elm architecture, so what that means, I will go into that again. And it supports composable views, and it has a lot of built-in structures like tables and forms and spinners and animations and so on and so forth, right? So it gives you a lot of TUI, components that you could potentially need, even though in the Gosh shell we are not using them, but they still get compiled in because it's a dependency, right? So that makes our life much, much easier to build a menu using that BubbleT library, because it comes with essentially no extra cost, right, in terms of footprint. Of course, the code that we're writing to kind of facilitate that boot menu, adds a little bit of more size to our init RunOS, but really the dependency, like the heavy dependency in there, which is BubbleT, doesn't do that. So, and that's pretty neat. So I started off using BubbleT to build my boot menu, right? And how BubbleT looks like, so I copied a couple of these examples from the website. It gives you list items, and you can add like tables, right? And here you can add like composable views. So that means we're all probably not designers, right, or web designers or this kind of web developers, but you have like a view, and you can put like multiple views into a single view, right? So that you can have something like tabs, and so on and so forth. So that's like pretty nice if you're building a boot menu. Okay, I said before that BubbleT uses the Elm architecture. And what is the Elm architecture, or what does that mean? Elm architecture essentially separates the model from the view and from the update process. So how that looks like is you for every composable view that you have an underlying model that kind of saves the data for you, and once you bring up that model, it kind of renders a UI, right? When you are in that UI, you can press a button, like tab, left, right, up, whatever, and that button press will trigger a message. That message will be sent through the BubbleT stack and lands in the update function of your own model, right? That update function kind of figures out what was that message, right? Was it a keystroke? Was it resizing of a window? Or what did it actually do? And it then updates the model, right? And exits again. Once the model has been updated, we will update the UI again and always go through that circle, right? So you have to keep that in mind when you're programming something in the Elm language, that you are separating the model from the view and the update process, because it always goes in that circle. And how that kind of looks like, I can show you. Okay, so how that looks like is, so this is kind of the the proof of concept stuff that I built for boot menu, and you essentially can see the composable views, right? So we have like a one big view with like the navigation bar on top where it says like dashboard and boot menu, and this is like that's like the outer view, let's say, and the inner view is basically what's in that rectangle, right? And now when we're pressing the tab key, we are, switching the view. And if we're looking at if we're thinking about the Elm architecture again that we just saw, right? We were pressing a button that was triggering a message that was updating the model, and that model was then rendering the view again, right? And that kind of happens under the hood now, and it also happens essentially when I go up and down. It does essentially the same, right? So I have like a pointer which points to what boot device do I have actually selected right now, and when I press a button, it sees, okay, I'm going down, so I have to increase my pointer on what is actually selected right now, and have to change on how the rendering looks like, right? Makes sense, right? It sounds very basic, but when you're working with that, it's kind of, for me, it was kind of complicated to get into that separation kind of thing. All right, so that was that. Oops. Okay, so I think we understand the Elm structure on how that kind of flows, and so when designing a boot menu, I was thinking about what do I need, right? And as I said before, I need these composable views, right? So I need like a navigation bar on top where I can kind of tap through, and I need like these inner views which kind of render what should ever be displayed there. And what should be displayed is, okay, we kind of probably need sensor readings somewhere, right? We probably want to build a dashboard or whatever, so that's important. We need a boot device selection, so we need to discover our boot devices and see what to boot and so on and so forth. And we probably need some BIOS options somehow, somewhere. And we need like a storage backend that saves those BIOS options somewhere. And I decided to so that were my requirements, right? So I need that composable view. I decided to separate basically the options that I'm displaying from the storage backend. So because the storage backend can be something differently depending on the underlying firmware that you have, right? So as we remember, Linux boot and the boot menu itself is pretty far in the boot process, right? So all the hardware installation already happened. So any BIOS option that I need to set kind of depends on what underlying firmware do I have, like what is actually initializing my hardware. So that needs to be separate from what BIOS options do I want to display. And so that means I separated that, and I made it pluggable and exchangeable, right? So I wrote a driver now for core boot that works with VPD data. However, for UEFI, you probably want to use UEFI variables to store these kind of things, right? For U-boot, you have like a different mechanism maybe. So that needs to be separated, and you need to inject those storage backends into each of these individual views. The views needs to be pluggable, obviously, right? So you have this composable views, and you want to be able to configure, what should be displayed there on top, right? Should I want to have a dashboard? What do I want to have BIOS options? Do I have a boot device selection or whatsoever? That comes kind of for free because BubbleT already takes care of this. That it gives you an interface which you have to implement in Golang in order to have these composable and pluggable views there. And so what I did until now, as I said, it's a side project, right? What I did until now is I've implemented the composable view, right? So I can add more views and delete more views if I want to. They are configurable through a configuration file that I set up. So you can basically define: do I want to have a dashboard? Do I want to have boot device selection? Do I want to have BIOS options? For the BIOS options, I'm using coreboot as an underlying firmware, and coreboot has a mechanism called SOT, which is System Option Table, I guess, the short form. And I'm pathing those BIOS options in from the coreboot SOT tables. So that means the BIOS options are essentially the stuff that you want to be able to configure in your BIOS, like PCIe, bifurcation maybe, right? Enable USB ports, and so on and so forth. And that kind of gets exposed through coreboot on what it is actually capable of configuring there. And that gets exposed through these SOT tables, and we have a parser for that. Now, I implemented the boot device selection, so that was like pretty straightforward because uroot already gives you something called local boot. And local boot is essentially discovering local hard drives and being able to boot into that, so I could easily leverage that. And as I said, I implement like the storage backend. So I separated the BIOS options, from what BIOS options do I have and what is the value of that BIOS options. I separated that and stored all the stuff in VPD, right, in Vital Product Data. So coreboot gives you an option to reserve a certain part of the flash where you can write these VPD, or where you can write into that VPD section, and there I'm essentially saving my BIOS options. So once coreboot reboots, or once I reboot the system, coreboot can pick up the stuff that is actually in the VPD section because it can read it and can configure it the way that I configured it in the boot menu. Okay, so what's still on my agenda, right? So I need a good project name. So that's like essentially the most important stuff. And I need to clean up stuff because that was like growing over the last couple of months on what I did there. In terms of functionality, I'm looking at implementing UFI variables as a storage backend. So currently, as I said, I'm only using coreboot as an underlying firmware. However, I want to see that I use UFI as an underlying firmware, and then I need to call the get variable and set variable runtime services that UFI provides there. Looking to other ways on how to parse the BIOS options, so what should be displayed. As Sheng already mentioned, there's this UPL effort that is there that could essentially be used to expose what is the underlying firmware actually capable of configuring. I still have to work on the dashboard, so that is still ongoing there. So you can find the code that I wrote under the NoElements repository if you want to. You can check that out. I have like a working branch, which is like fix-up boot, that has the latest state in there that kind of works right now. If you want to know more about uroot, there's like a website, uroot.org, which you can check out and can have a closer look at too. You can have a look at BubbleT, which is like the terminal UI library that you can use for building such menus. And you can join our Slack, so we have like an open source firmware Slack. You have to get an invitation first for the Slack, but it's like self-inviting. So you can go on slack.osfw.dev, punch in your email address, and you will get an email on how to join our Slack channels. And there you can basically talk to everyone who's working on open source firmware. There are something like 1,500 people registered on that Slack, so there's quite some people that hang around there. And I guess that's it, right? Thanks for listening. And if you got any questions, feel free to hit me up. Thank you.